Armando mentioned, I'm filling in for Professor Grutter, which couldn't make it. So Professor Grutter is CEO of Nanoacademic Technologies. I'm the Atomistic director. And yeah, we'll be talking about AFM and STM simulation that we can do with our software tools. So let me briefly introduce what is Nanoacademic Technologies and what we do, and then I'll just introduce the product that we use for this kind of simulation, which is called RESCU, and then I will delve into the applications in question, and then present a little summary and outlook. So Nanoacademic Technology, it was founded in 2008 by Professor Grutter and two other co-researchers, and we're located in Montreal, in Quebec, Canada, and we're just by McGill University across the corner. And so, as you will see, what I will present is a research collaboration done in the physics department. This is a brief overview of our team. So we're basically a bunch of physicists plus a couple software developers, and we recently hired a sales and marketing director who's attending. And yeah, so what do we do exactly? So we write code that will start from first principle. So we try to simulate materials and devices from their atomic structure with the least parameter and user intervention possible to have the most predictive value possible. I've listed here a few of the products we distribute. So NanoDecal is mostly specialized for device calculation, and RESCU for material research. And we're coming up with a new product called QTCAD, which is also for device characterization, but dealing more with quantum technology applications. So there are several approaches in material design. I think a lot of people here are experimentalists, so they do run things in the real world with big machines like this one. And so that's one way to explore the possibilities of modern nature. At Nanoacademic, we focus on three other branches. There is a bona fide theory, so equations and stuff. What I'm mostly interested in is modeling. So what can you do with computers, basically trying to bring theories alive in real settings. And also we have another division dealing with material informatics. So experimentalists in particular to produce a lot of data, and sometimes it is helpful to use computers to try to tap in these massive amount of data and try to find out interesting materials or predict properties of materials based on certain measurements. So one thing that we do a lot of with modeling too, and you may be familiar with a lot of software that are specialized for studying specific materials. So for example, you have like an H-beam of iron or something like that, and then you want to know how much it bends. Usually you have to go back and look at some parameters and tables, and that will tell you how the beam will bend. So what we do is, from the atomic structure of the material itself, we can derive and calculate the value for these parameters instead of having to measure them in the lab. Okay, so let me just touch a word on why do we need a DFT solver, in particular one that handles thousands of atoms. So this is a table of all sorts of electronic structure theory and other kind of theory for studying materials. You have molecular dynamics for screening force field, which may be familiar to some of you. And on the other side, like on the lower end of the x-axis, you have so-called quantum chemistry method, DFT, and linear scaling DFT. DFT is mainly what we do. We also implement hybrid DFT, and the trade-off here is number of atoms you can simulate versus transferability of the method. So transferability means you can simulate a lot of different materials and systems without having to fiddle too much with parameters. So DFT is good in that you can go to the atom level and get some prediction on an atom, and up to 1,000 atoms. Hybrid DFT is a little bit more predictive, but also more expensive. And but unfortunately, most of the interesting problems nowadays, you know, you go into biology, you know, large devices, materials have complexified, so the smallest unit cell that you have to simulate includes a lot of atoms, and then you can tackle these with traditional DFT code. But at Nanoacademic, we have developed a method and a code that can deal with much larger system, and so we can routinely on the modest computer cluster deal with system over 10,000 atoms in DFT and more than 1,000 atoms in hybrid DFT. So this is the main reason and purpose why RESCU was developed. So it's a so-called large-scale DFT solver. It was written in MATLAB, and the implementation and design focuses on large-scale systems. And you can study really a vast range of property and system with it. So you can access spintronics properties, phonons, optical properties, and all sorts of electronic structure derived quantities. Okay, so again, why do we need to simulate these large systems in DFT? Well, what we're interested in at Nanoacademic is like the functionality of materials. And you know, on the one hand, you have materials nowadays that do include a lot of atoms, often more than 10,000, but really its properties are dependent sometimes on a single atom being added or removed from the structure. On the other hand, there's traditional engineering technique where you have to feed in some device parameter and do a lot of fitting, and you can sometimes get the answer down the line. But once you start shrinking the device size from the 100 nanometer scale to what it is nowadays with less than sub 10 nanometer scale, it becomes extremely difficult because of all sorts of quantum interference effect to just do semi-empirical device modeling. So we're basically at the bridge of those two, let's say, academic traditional method like NEGF DFT and engineering, and that's where we locate ourselves. So basically promoting what was done in academia to some full-fledged CAD software. So for device simulation, a pretty complex structure always includes a lot of atoms nowadays, so you will need to calculate those large systems. In energy research, you have a ton of material that you're often dependent on, you know, adding a dopant here and there, and then that's going to completely realign the bands and the water splitting or CO2 splitting properties of your material. And so you need to simulate large supercells to access the kind of dilution factor for catalyst that you find in the lab. So that's also a very challenging simulation problem. Material chemistry, so people are interested like build molecule, forming some chiral structure on surfaces. You have to study water material interfaces nowadays. That's of much interest. And of course, what seems to be the topic of the day, surface science. So for surface science, again, you will see all sorts of effects where individual atoms or the atomic structure is visible in the data, but it's pretty hard to simulate because you have like long range structure. So that often happens on surfaces where you have long range reconstruction in semiconductors. And for example, in AFM, as I will discuss, you do need to include a lot of atoms in simulation, in particular the tip, to get certain quantities right. Okay, so let me jump into one study that was done, in collaboration with experimentalists at McGill University. So I'm first going to focus on AFM, but we actually did a study on general scanning probe microscopy. So yeah, you know that well. This is a very important experimental technique that awarded the Nobel Prize to Benning and Rohrer. So the difficulty of studying surfaces with STM and AFM and trying to compare that with simulation results is often because simulation results are highly dependent on the atomic structure of the tip, and with different tip, you will get different STM and AFM images. So these are two series of images taken for.
Hello.
Hello? Yeah, taken for different tips in these two publications, and you can see that the final image show much different patterns, and that is generally attributed to difference in the tip. So what we got from experimentalists at McGill University, Megan Cowie, who did her master thesis there with Peter Grutter, is the structure for a tip. So they use field ion microscopy to basically get this kind of image for the tip, and I will show how. But they were able to image some tips with this technique and basically get precise position for every atom in the tip. So that's usually what we need to get started. After that, DFT is predictive enough to relax the final structure and the substrate. So this is the actual image that Megan got. You can see different planes in the tip that you can identify from the relative position of the atoms. And with some hypothesis, basically that this tungsten tip is crystalline, so these are actual crystal planes, and that the tip is roughly spherical. With some criterion, she was able to generate all the possible spheres that have a radius close to 120 nanometer, and using 6 criteria, basically determine uniquely what the atomic structure of the tip was. And this yields the atomic coordinates for this. To our knowledge, this was not done before. In the literature, there's a lot of simulation of AFM and STM. Usually they are limited to approximating the whole tip as a single atom, or often 3 atoms, like they would in this case. And as I would show, this is not sufficient. All right, so this is just a picture of the kind of structure we have to simulate. So as I was mentioning, well, in the end, this tip is pretty big, must include a lot of atoms, and the surface, of course, needs to be commensurate with that. So you also need to include a lot of atoms. So the kind of calculation we're talking about is like plus 3,500 atoms, tens of thousands of electrons, and you need to be able to do this kind of calculation repeatedly because you're going to study, for example, the force as a function of distance at different spots on the surface. Okay, so the first thing Xiaodong checked was the good thing with these simulations. You can basically decompose the forces on the whole tip into their contribution on every atom. So what he found is that if you include a single layer, which is the ideal triatomic tip that is typically used in the literature, you much underestimate the magnitude of the forces that is applied on the tip and the surface. And he was able to show that you really have to go to the equivalent of 3 or more layers to get a well-converged value for the force on the tip as a function of distance. For this particular case, he was able to estimate that a kind of rule of thumb correction as a function of distance was like minus 75% at 2 angstrom and 30 at 3 angstrom. So technically, you could use that as maybe a rough order of magnitude correction. So he did the study and tried to decompose the force at various spots on the surface. So depending where you are, the forces decompose differently, similarly with the binding energy. And the data that was derived by McGill and Cowie showed that our prediction using the real tip, unlike the ideal triatomic model, does fit the data perfectly, basically from large separation down to about 2 angstrom. After that, you can see a discrepancy that basically originates in the fact that at this short distance, there's a large-scale relaxation occurring as the tip kind of goes close to the surface, and that's not taken into account in our model. All right, so in summary, we are able to do this kind of calculation. It is necessary to simulate a pretty large section of the tip if you want the right forces and match the experimental results. And the AFM image itself is dominated by the first layer, so you could get something right by doing a triatomic model. But if you want other quantities like the strain of force and observe the symmetry effect, which is having different binding energy depending on where your tip is relative to the surface, you will need to simulate more layers. That's also true for knowing the impacts of defect. I think I'm pretty much out of time, so let me just really skim over this section. So we also have a feature where we can calculate the current in STM. In STM, the tip is also a major factor in the experimental data. So here it's showing 2 different tips and completely different voltage versus current curve depending on the tip. And we implement a self-consistent Bardeen approach where we actually calculate the whole system, and we're able to split the wave functions for the whole system into tip and surface wave function, and then compute the tunneling current between the tip and sample according to this Bardeen theory. Um, okay, so these are results. So let me just skip over that and just summarize the study. So basically, Miguel Cowie, working for Professor Grutter, was able to precisely image a tip using this field ion microscopy. And then based on that, we're able to run a simulation with the real experimental tip coordinates. And this allows us to derive a series of results that match much better the experimental data than the ideal triatomic model would do. And also this definition of the tip profile is also important in STM, where the mapping of the current versus voltage on the surface is strongly dependent on the atomic structure of the tip. Okay, so that's one example of application of RESCU. We are working on tons of topics like this kind of device, organic solar cells, lead materials, and yeah, etc. MRAM, CPU interconnects, and yeah, I'm glad to be here. And if you reach out to us with some suggestions, I'll be happy. So this work has been contributed by a lot of people listed here, and some computing facilities in Canada. So let me end here, and thank you very much for your attention.